Okay, so what if we have kind of another kind of inhibition, but this time it's not really inhibition. It's more of a pH effect on enzyme kinetics. So what you can do is you can modify your enzyme kinetics, and what if you have, the formation, either the formation of H plus ions, or using up the H plus ions to form a complex. And it really depends, which way you read this will depend on whether or not it's a weak or strong acid, or if it's like a more basic, depending on whether it releases or if it absorbs H plus ions, and that kind of stuff. So we can model this in the same way as we have been doing modeling for the product formation rate. And you'll see it's, again, same thing, just a lot of complexes involved, but it's not actually complex itself. Okay then. Let's start off with the product formation rate. And it's just going to be K2 times this complex. And we can write, using the fast equilibrium assumptions, wherever there's a double arrow, the forward rate equals the backwards rate. So I'm going to be calling this one capital K1 and this one's capital K2. Don't mix up lowercase k2 with capital K2. They're different. Okay, good. And then we can write the enzyme conservation equation. Whoops. Actually, in this case, we don't have ES, it's E minus. So sorry, that's going to be E minus, that's EH, because the notation here is a little bit different. And we substitute everything in. This looks... Well, see now you have a whole bunch of complexes in each equation, so the best thing we can do is isolate in terms of EH, and then substitute in the results for these ones to get those two complexes. Oh, whoops. EH, sorry, okay, and then... Okay, and then just solve for the other ones, just to get this. And then there was another one. And then we can double check that to make sure we didn't make any arithmetic mistakes. It looks fine to me. And we just put them into the enzyme conservation equation, and I'll just do this in one step. And remember, there's a big K's on the bottom. That's supposed to be a plus. Okay. And we substitute them back into the K2 EHS, and we solved for EHS as well already, so we plug it all back in. Gotta be careful with little k though. Don't mix it up. EHS is okay. And we substitute. Okay, and then we just simplify it. I think we can take the usual approach, just distribute those throughout the bottom. And we just keep doing it. And we can, factor out the Michaelis constant. It looks a little weird, but let's keep going. Okay. Now I see what I can do, actually. Now we can divide everything by H plus. Which is just the same thing as multiplying by 1. Just gotta make sure you do it for all sides. So the 1 comes from dividing this one out. Okay, good. And then we'll just have S on that side. And then we'll so that we can get the Michaelis Menton formula, Vm equals K2E naught. That's the same as no inhibition. And then the bottom one is gonna be apparent because now we have all this extra stuff. And then we'll get in the Michaelis Menton form. Looks nice. And there you go. That's what the effect of pH will have on your enzymatic reaction. Now, bear in mind that it depends on what enzymes you're using. This might this model might not apply depending on what kind of enzyme you're using, because some enzymes will just break completely, and that's what's going to happen in most cases. Enzymes, they have a very well-defined range. You need to look up what you're using in literature, and chances are if you're trying to modify the pH, you're going to be messing up your system. It's either you're dealing with a system that has mostly normal conditions, like, pH of regular water, this kind of stuff, or you're dealing with something that is a very exceptional case, like maybe you're dealing with bacteria or something that have very high or very low pH, like either very acidic or very alkaline conditions. But in most cases, it's not like you can really improve your efficiency. It's like, if you're working with certain enzymes, you'd know then that you need to use a low pH, or you'd have to be using like water pH or something like that. But yeah, still, like, this equation can sometimes show some of the nuances of what happens to your enzymes. Let's say your enzyme doesn't get completely denatured from changing the PS, then perhaps it will follow these kinds of kinetics. And yeah, you just use these things, and you can find most of these values in literature. And there you go. Hope you enjoyed the video.